In this lecture, I will present some fundamentals about renewable energy, particularly about solar energy. Basically, all the forms of energy in the world, as we know, it are solar in origin. Oil, coal, natural gas and wood were originally produced by photosynthesis process, followed by complex chemical reactions in which decaying vegetation is subjected to very high temperatures and pressures over a long period of time. Even the energy of the wind has a solar origin, since it is caused by difference in temperature in various regions of the Earth. The great advantage of solar energy compared with other forms of energy is that it is clean and can be supplied without environment pollution. Over the past century, fossil fuels provided most of our energy because these were much cheaper and more convenient than energy from alternative energy sources, and until recently, environment and pollution has been of little concern. The main problem is that proven reserves of oil and gas at current rates of consumption will be adequate for meet demand for only another 42 and 54 years respectively. The reserves of coal are in a better situation. They will be adequate for at least the next 100 years. If we try to see the implications of these limited reserves, we are faced with a situation in which the price of fuels will accelerate as the reserves are decreased. Considering that the price of oil has become firmly established as the price leader of all fuel prices, the conclusion is that energy prices will increase continuously over the next decades. In addition, there is growing concern about the environment pollution caused by burning fossil fuels. Many alternative energy sources can be used instead of fossil fuels. The decision as to what type of energy source should be utilized in each case must be made on the basis of economic, environmental and safety considerations. Because of the desirable environmental and safety aspect, it is widely believed that solar energy should be utilized instead of other alternative energy forms, because it can be provided sustainably without harming the environment. If the world economy expands to meet the expectations of countries around the globe, energy demand is likely to increase, even if laborious efforts are made to increase the energy use efficiency. It is now generally believed that renewable energy technologies can meet much of the growing demand at prices that are equal to or lower than those usually forecast for conventional energy. The growing evidence of environmental problems is due to a combination of several factors, since the environmental impact of human activities has grown dramatically. This is due to the increase of the world population, energy consumption, and industrial activity. Achieving solutions to the environmental problems that humanity faces today requires long-term potential actions for sustainable development. In this respect, renewable energy resources appear to be one of the most efficient and effective solutions. Solar energy is the oldest energy source ever used. The sun was adored by many ancient civilizations as a powerful god. The first known practical application was in drying for preserving food. The very first applications of solar energy refer to the use of concentrating collectors, which are, by their nature and the requirement to follow the sun, more difficult to apply. During the 18th century, solar furnaces capable of melting iron, copper, and other metals were being constructed for polished iron, glass lenses, and mirrors. One of the first large-scale applications was the solar furnace built by well-known French chemist Lavoisier, who around 1774 constructed powerful lenses to concentrate solar radiation. This attained the remarkable temperature of 1760 degrees Celsius. The furnace used a 1.32 meters length plus a secondary 0.2 meter length to obtain such temperature, which turned out to be the maximum achieved for 100 years. Another application of solar energy utilization in this century was carried out by the French naturalist Buffon, who experimented with various devices that he described as hot mirrors burning at long distance. During the 19th century, attempts were made to convert solar energy into other forms based upon the generation of low-pressure steam to operate steam engines. Auguste Mouchot pioneered this field by constructing and operating several solar-powered steam engines between the years 1864 and 1878 in Europe and North Africa. The solar energy gained as used to produce steam to drive a printing machine. Becquerel discovered the photovoltaic effect in selenium in 1839. The first practical application of solar cells was in space, where cost is not a barrier, since no other source of power is available. The PV cells are packed into modules that produce a specific voltage and current when illuminated. PV modules can be connected in series or in parallel to produce larger voltage or currents. PV systems can be used independently or in conjunction with other electrical power sources. Applications powered by PV systems include communications, both on Earth and in space, remote power, remote monitoring, lighting, water pumping, and battery charging. The two basic types of PV applications are the standalone and the grid-connected systems. Standalone PV systems are used in areas that are not easily accessible or have not access to main electricity grids. A standalone system is independent of the electricity grid, with the energy produced normally stored in batteries. A typical standalone system would consist of PV module or modules batteries, and a charge controller. An inverter may also be included in the system to convert the direct current generated by the PV modules to the alternating current form required by normal appliances. In the grid-connected applications, the PV system is connected to the local electricity network. This means that during the day, the electricity generated by the PV system can either be used immediately, which is normal for systems installed in office and other commercial buildings, or sold to an electricity supply company, which is more common for domestic systems, where the occupier may be out during the day. In the evening, when the solar system is unable to provide the electricity required, power can be bought back from the network. In effect, the grid acts as an energy storage system, which means the PV system does not need to include battery storage. When PV started to be used for large-scale commercial applications about 20 years ago, the efficiency as well below 10%. Nowadays, the efficiency has increased to about 15%. Laboratory or experimental units can give efficiencies of more than 30%, but these have not been commercialized yet. Another area of solar energy is related to passive solar buildings. The term passive solar is applied to buildings that include, as integral parts of the building, elements that emit, absorb, store and release solar energy, and thus reduce the need for auxiliary energy for comfort heating. The elements have to do with the current orientation of buildings, the correct sizing of openings, the use of overhangs and other shading devices, and use of insulating and thermal mass. Before the advent of mechanical heating and cooling, passive solar buildings design was practiced for thousands of years as a means to provide comfortable indoor conditions and protect inhabitants from extreme weather conditions. People at those times considered factors such as solar orientation, thermal mass and ventilation in the construction of residential dwellings, mostly by experience and the transfer of knowledge from generation to generation. This section briefly reviews other renewable energy systems. Wind is generated by atmospheric pressure differences driven by solar power. In terms of capacity, wind energy is the most widely used renewable energy source. Today, there are many wind farms that produce electricity. Wind energy is in fact an indirect activity of the sun. Its use as energy goes as far back as 4,000 years, during the dawn of historical times. It was adored, like the sun, as a god. For the Greeks, wind as the god Aeolus, the flying man. In the beginning, wind energy was used for propulsion of sailing ships. In antiquity, this was the only energy available to drive ships sailing in Mediterranean basin and other seas, and even today it is used for sailing small leisure boats. A use of wind power as connected to the invention of the water pump and used extensively originally by farmers in the United States and subsequently in many parts of the world. This is of the classic lattice metal tower carrying a rotor made from galvanized steel vanes known as the Californian type wind pumps. The technology of the wind turbines generators currently in use is only 25 years old, and the investment is in it so far has been rather modest compared with other energy sources. Nearly all the wind turbines manufactured by industry are of the horizontal axis type, and most of them have a three-bladed rotor. However, for some years now, machines have been constructed with two blades to reduce the costs and prolong the life of machines by making them lighter and more flexible by reducing the number of high-technology components. Biomass energy is a generic term applied to energy production achieved from organic material broken down into broad categories: wood biomass, forestry, timber, residues and co-products, other woody material including thinning and cleaning from woodlands, untreated wood products, energy crops such as willow, short rotation coppice and miscanthus. The other category, non-woody biomass, like animal wastes, industrial and biodegradable municipal products from food processing, and high-energy crops such as rape, sugar cane and corn. Biomass, mainly in the form of industrial and agricultural residues, provided electricity for many years with conventional steam turbine power generators. Existing steam turbine conversion technologies are cost competitive in the regions where low-cost biomass fuels are available, even though these technologies are comparatively inefficient as the small sizes required for biomass electricity production. The performance of biomass electric systems can be improved dramatically by adapting to biomass advanced gasification technologies, developed originally for coal. Biomass is a more attractive feedstock for gasification than coal because it is easier to gasify and has very low sulfur content. Therefore, expensive sulfur removal equipment is not required. Measurements show that the ground temperature below a certain depth remains relatively constant throughout the year. This is because the temperature fluctuations at the surface of the ground are diminished as the depth of the ground increases to the high thermal inertia of the soil. These are different geothermal energy sources. They may be classified in terms of the measured temperature as low, medium and high temperature. The thermal gradient in the Earth varies between 15 and 75 degrees per kilometer deep. Nevertheless, the heat flux is anomalous in different continental areas. Geothermal power based on current hydrothermal technology can be locally significant in those parts of the world where there are favorable resources. In these systems, ground heat exchangers are employed to exchange heat with the ground. The ground can be used as an energy source and energy sink or for energy storage. For the efficient use of ground in energy systems, its temperature and other thermal characteristics must be known. Studies show that the ground temperature varies with depth. At surface, the ground is affected by short-term weather variations, changing to seasonal variations as the depth increases. At deeper layers, the ground temperature remains almost constant through the seasons and the years, and is usually higher than that of the ambient air during the cold months of the year, and lower during the warm months. The ground, therefore, is divided into three zones: the surface zone, where hourly variation of temperature occurs; the shallow zone with monthly variations; and the deep zone, where the temperature is almost constant year-round. The structure of physical properties of the ground are factors affecting temperature in all zones. The temperature of the ground is a function of thermal conductivity, specific heat density, geothermal gradient, water content, and water flow rate through the ground. Ground heat exchangers or earth heat exchangers are devices used for the exploitation of the ground thermal capacity and difference in temperature between ambient air and ground. A ground heat exchanger is usually an array of buried pipes installed either horizontally or vertically into the ground. They use the ground as a heat source when operating in the heating mode, and as a heat sink when operating in the cooling mode, with the fluid, usually air, water, or a water antifreeze mixture, to transfer the heat from or to the ground. They can contribute to the air conditioning of a space, for water heating purposes, and also for improving the efficiency of a heat pump. Ground-coupled heat pumps or geothermal heat pumps are systems combining a heat pump with a ground heat exchangers for the heat exchange process, which improves the heat pump efficiency. Mainly, they are of two types, namely the ground-coupled, a closed-loop system, or the groundwater open-loop system. The type to be used is chosen according to the ground thermal characteristics, the available land for installing, and the groundwater availability and temperature. As observed from the Earth, the Sun disk forms an angle of 32 minutes of a degree. This is important in many applications, especially in concentration optics, where the Sun cannot be considered as a point source, and even this small angle is significant in the analysis of the optical behavior of the collector. As observed from Earth, the path of the Sun across the sky varies throughout the year. Knowledge of the Sun's path through the sky is necessary to calculate the solar radiation falling on a surface, the solar heat gain, the proper orientation of solar collectors, the placement of collectors to avoid shading, and many more factors. The general weather of a location is required in many energy calculations. This is usually present as a typical meteorological year file. In solar energy calculations, apparent solar time must be used to express the time of day. Apparent solar time is based on the apparent angular motion of the Sun across the sky, the time when the Sun crosses the meridian, and the observer is the local solar noon. It usually does not coincide with the 12 o'clock time of a locality. To convert the local standard time to apparent solar time, two corrections are applied: the equation of time, ET, and longitude correction. These are analyzed next. Due to factors associated with the Earth's orbit around the Sun, the Earth's orbital velocity varies throughout the year, so the apparent solar time varies slightly from the mean time kept by a clock running at a uniform rate. The variation is called the equation of time. The equation of time arises because the length of a day, that is, the time required by the Earth to complete one revolution about its own axis with respect to the Sun, is not uniform throughout the year. Over the year, the average length of a day is 24 hours. However, the length of a day varies due to the eccentricity of the Earth's orbit and the tilt of the Earth's axis from the normal plane of its orbit. Due to ellipticity of the orbit, the Earth is closer to the Sun on January 3 and further from the Sun on July 4. Therefore, the Earth's orbiting speed is faster than its average speed for half the year, from about October through March, and slower than its average speed from the remaining half of the year, from about April through September. The values of the equation of time as a function of the day of the year and can be obtained approximately from the following equation. A graphical representation of the equation of time is shown in figure, from which the equation of time can be obtained directly. The standard clock time is evaluated from a selected meridian near the center of a time zone or from the standard meridian, the Greenwich, with this at longitude of 0 degrees. Since the Sun takes 4 minutes to traverse 1 degree of longitude, a longitude correction term of 4 plus should be either added or subtracted to the standard clock time of the locality. This correction is constant for a particular longitude, and the following rule must be followed with respect to sign convention. If the localization is east of the standard meridian, the correction is added to the clock time. If the location is west, it is subtracted. The general equation for calculation the apparent solar time is if a location is east of Greenwich, the sign of equation is minus, and if it's west, the sign is plus. If a daylight saving time is used, this must be subtracted from the local standard time. The term daylight saving depends on whether daylight saving time is in operation, usually from end of March to end of October or not. This term usually ignored from this equation and considered only if the estimation is within the daylight saving period. The eccentricity E of the Earth's orbit is very small. Therefore, the orbit of the Earth around the Sun is almost circular. The Sun-Earth distance r at perihelion, the shortest distance at January 3, and aphelion, the longest distance at July 4, is given by r, by the equation, where a is the mean Sun-Earth distance. The plus sign in equation is for the Sun-Earth distance, when the Earth is at the aphelion position, and the minus sign for the perihelion position. The Sun's position in the sky changes from day to day and from hour to hour. It is common knowledge that the Sun is higher in the sky in the summer than in winter. The relative motion of the Sun and Earth are not simple, but they are systematic and thus predictable. Once a year, Earth moves around the Sun in an orbit that is elliptical in shape. As the Earth makes its early revolution around the Sun, it rotates every 24 hours about its axis, which is titled as an angle of 23.45 degrees to the plane of the ecliptic, which contains the Earth's orbital plane and the Sun's equator, as shown in the figure. The most obvious apparent motion of the Sun is that it moves daily in an arc across the sky, reaching its highest point at midday. As winter becomes spring and then summer, the sunrise and sunset points move gradually northward along the horizon. In the northern hemisphere, the days get longer as the sun rises early and sets later each day, and the sun's path gets higher in the sky. On June 21, the Sun is at its most northerly position with respect to the Earth. This is called the summer solstice, and during this day, the daytime is at a maximum. 6 months later, on December 21, the winter solstice, the reverse is true, and the Sun is at its most southerly position. In the middle of the 6 months range, on March 21 and September 21, the length of the day is equal to the length of the night. These are called spring and fall equinoxes, respectively. The Ptolemaic view of the Sun's motion is used in the analysis that follows. for simplicity. That is, since all motion is relative, it is convenient to consider the Earth fixed and to describe the Sun's virtual motion in the coordinate system fixed to the Earth with its origin at the site of interest. As the Earth rotates around the Sun, is it as if the polar axis is moving with respect to the Sun. The solar declination is the angular distance of the Sun's rays north or south of the equator. North declination designed as positive. As shown in figure, it is the angle between the Sun-Earth center line and the projection of this line on the equatorial plane. Declinations north of the equator are positive and those south are negative. The variation of the solar declination throughout the year is shown in figure. The declination in degrees of any day of the year n can be calculated approximately by the equation. The hour angle of a point on the Earth's surface is defined as the angle through which the Earth will turn to bring the meridian of the point directly under the Sun. The hour angle at local solar noon is 0, with each 360 divided for 24 hours or 15 degrees of longitude equivalent to 1 hour. Afternoon hours behind designed as positive. Expressed symbolically, the hour angle in degrees and h, where the plus sign applies to afternoon hours and the minus sign to morning hours. The hour angle can also be obtained from the apparent solar time, that is, the correct local solar time. At local solar noon, apparent solar time 12 o'clock and h equal 0 degree. Therefore, from equation, the local standard time is the solar altitude angle is the angle between the Sun's rays and a horizontal plane, as shown in the figure. It is related to the solar zenith angle, which is the angle between the Sun's rays and the vertical. Therefore, the mathematical expression for the solar altitude angle is where L it's the local latitude, defined as the angle between a line from the center of the Earth to the site of interest and the equatorial plane. Values north of the equator are positive and those south are negative. Solar azimuth angle is the angle of the Sun's rays measured in the horizontal plane from due south, the true south, for the northern hemisphere or due north for the southern hemisphere. westward is designated as positive. The mathematical expression for solar azimuth angle is at solar noon. By definition, the Sun is exactly on the meridian, which contains the north-south line, and consequently the solar azimuth is 0 degree. Therefore, the noon altitude is the solar incidence angle is the angle between the sun's rays and the normal on a surface. For a horizontal plane, the incidence angle and the zenith angle are the same. The angles shown in figure are related to the basic angles. For practical purposes, instead of using the preceding equations, it is convenient to have the sun's path plotted on a horizontal plane, called a sun path diagram, and to use the diagram to find the position of the sun in the sky at any time of the year. The solar altitude angle and the solar azimuth angle are functions of latitude, hour angle and declination. In a two-dimensional plot, only two independent parameters can be used to correlate the other parameters. Therefore, it is usual to plot different sun path diagrams for different latitudes. Such diagrams show the complete variation of hour angle and declination for a full year. Figure shows the sun path diagram for 35 degrees north latitude. Lines of constant declination are labeled by the value of the angles. Points of constant hour angles are clearly indicated. All substances, solid bodies as well as liquids and gases above the absolute zero temperature emits energy in the form of electromagnetic waves. The radiation that is important to solar energy applications is that emitted by the sun within the ultraviolet, visible and infrared regions. Therefore, the radiation wavelength that is important to solar energy application is between 0.17 and 3 . A number of radiation parameters are needed for the design, sizing, performance evaluation and research of solar energy applications. These include total solar radiation, beam radiation, diffuse radiation and sunshine duration. Various types of equipment measure the instantaneous and long-term integrated values of beam, diffuse and total radiation incident on the surface. This equipment usually employs the thermoelectric and photovoltaic effects to measure the radiation. There are basically two types of solar radiation measuring instruments: the pyranometer and the pyrheliometer. The former is used to measure total, beam and diffuse radiation within its hemispherical field of view, whereas the latter is an instrument used for measuring the direct solar irradiance. The pyranometer can also measure the diffuse solar radiation if the sensing element is shaded from the beam radiation. The operation of solar collectors and system depends on the solar radiation input and the ambient air temperature and their sequences. One of the forms in which solar radiation data are available is on maps. These give the general impression of the availability of solar radiation without details on the local meteorological conditions, and for this reason must be used with care. One valuable source of such information is the Meteonorm website. Solar energy collectors are special kinds of heat exchangers that transform solar radiation energy to internal energy of the transport medium. The major component of any solar system is the solar collector. This is a device that absorbs the incoming solar radiation, converts it into heat, and transfers the heat to a fluid, usually air, water, or oil, flowing through the collector. The solar energy collected is carried from this circulating fluid either directly to the hot water or space conditioning equipment or to a thermal energy storage tank, from which it can be drawn to use at night or on cloudy days. There are basically two types of solar collectors: non-concentric or stationary and concentric. A non-concentric collector has the same area for intercepting and absorbing solar radiation, whereas a sun-tracking concentrating solar collector usually has concave, reflecting surfaces to intercept and focus the sun's beam radiation to a smaller receiving area, thereby increasing the radiation flux. Concentration collectors are sustainable for high temperature applications. Solar collectors can also be distinguished by the type of heat transfer liquid used: water, non-freezing liquid, air, or heat transfer oil, and whether they are covered or uncovered. Solar energy collectors are basically distinguished by their motion: stationary, single-axis tracking, and two-axis tracking, and the operating temperature. First, we'll examine the stationary solar collectors. These collectors are permanently fixed in position and do not track the sun. Three main types of collectors fall into this category: flat plate collector, stationary compound parabolic collector, evacuated tube collector. A typical flat plate collector is shown in figure. When solar radiation passes through a transparent cover and impinges on the Blackner observer surface of high absorptivity, a large portion of this energy is absorbed by the plate and transferred to the transport medium in the fluid tubes, to be carried away for storage or use. The underside of the observer plate and the two sides are well isolated to reduce conduction losses. The liquid tubes can be welded to the absorbing plate or they can be an integral part of the plate. The liquid tubes are connected at both ends by large diameter header tubes, The header and the riser collector is the typical design of flat plate collectors. An alternative is the serpentine design shown in figure. This collector does not present the potential problem of uneven flow distribution in various riser tubes of the header and riser design, but serpentine collectors cannot work effectively in thermosyphon mode, the natural circulation, and need a pump to circulate the heat transfer fluid. The absorber plate can be a single sheet on which all risers are fixed, or each riser can be fixed on a separate fin. The transparent cover is used to reduce convection losses from the absorber plate through the restraint of the stagnant air layer between the absorber plate and the glass. It also reduces radiation losses from the collector because the glass is transparent to the shortwave radiation received by the sun, but it is nearly opaque of long waves thermal radiation emitted by the absorber plate. It's the greenhouse effect. The advantage of flat plate collectors are that they are inexpensive to manufacture. They collect both beam and diffuse radiation, and they are permanently fixed in position, so no tracking of the sun is required. The collector should be oriented directly toward the equator, facing south in the northern hemisphere and north in the southern hemisphere. The optimum tilt angle of the collector is equal to the latitude of the location, with angle variation of 10 to 50 degrees more or less, depending on the application. If the application is solar cooling, then the optimum angle is latitude minus 10 degrees, so that the sun will be perpendicular to the collector during summertime, when the energy will be mostly required. If the application is space heating, then the optimal angle is latitude plus 10 degree, whereas for annual hot water production it is latitude plus 5 degree, to have relatively better performance during winter time when hot water is mostly required. The main components of a FPC, as shown in figure, are the following: cover, heat removal fluid passageways, absorber plate, headers and manifolds, insulating, e container. This figure shows a number of absorber plate designs for solar water and air heaters that have been used with varying degrees of success. A shows a bonded sheet design in which the fluid passages are integral to the plate to ensure good thermal conduct between the metal and the fluid. Figure B and C show fluid heaters with tubes soldered, brazed, or otherwise fastened to upper or lower surface to sheets or strips of copper. Copper tubes are used most often because of their superior resistance to corrosion and high thermal conductivity. Compound parabolic collectors are non-imaging concentrators. They have the capacity of reflecting to the observer all of the incident radiation within wide limits. The necessity of moving the concentrator to accommodate the changing solar orientation can be reduced by using a trough with two sections of a parabola facing each other as shown in figure. Compound parabolic concentrators can accept incoming radiation over a relatively wide range of angles. By using multiple internal reflections, any radiation entering the aperture within the collector acceptance angle finds its way to the observer surface located at the bottom of the collector. The observer can take a variety of configurations. It can be flat, bifacial, edged, or cylindrical, as shown in figure. Conventional, simple flat plate solar collectors were developed for use in sunny, warm climates. Their benefits, however, are greatly reduced when conditions become unfavorable during cold, cloudy, and windy days. Furthermore, weathering influence such as condensation and moisture cause early deterioration of internal materials, resulting in reduced performance and system failure. Evacuated heat pipe solar collectors tubes operate differently than the other collectors available on the market. These solar collectors consist of the heat pipe inside a vacuum sealed tube, as shown in figure. In actual installation, many tubes are connected to the same manifold as shown in figure in the right side.